So in the last video, I made this linear algebra assertion, this statement. When lambda 1 is different from lambda 2, these two functions are linearly independent. If you're curious as to, in more detail, what that means and why it's true, then you can watch this video. Otherwise, I'll consider this one to be optional, and you can skip to the next video. Okay, so first of all, what exactly is meant by linearly independent for functions? Well, we're treating functions as vectors here. So when I make these doodles where I'm like, drawing vectors as arrows, that might be a little bit misleading. Like in the doodle, you're thinking of the arrows as, column vectors or something with numerical coordinates that describe their location, right? Something like 1, 2, 2, 1, or something like that. But these are functions. So how am I thinking of these as vectors? Well, in linear algebra, the theory of linear algebra applies to any situation where you have objects that can be added and scaled in ways that satisfy the rules of vector spaces. So as long as the rules of vector spaces are satisfied by a collection of objects that you're looking at, you can apply the theory of linear algebra regardless of whether they happen to be things you can write as column vectors or whether they look like something totally different in their form. So that's the beauty of having a general mathematical theory, is that it can apply to situations that you maybe didn't have in mind when you created the theory. Maybe when you created the theory, you were thinking of column vectors and matrices, but then because the theory has some generality to it, you find later that all of the ideas apply to a totally different situation where your old pictures don't necessarily make sense anymore, but the results still apply. And in fact, you might still be able to make use of the pictures because of that, since there is a strong analogy. So this is the situation we're in. And so because functions of t, so the idea is functions of t in general, are vectors. Because we can think of them as vectors, because we can add functions of t, you can add two functions, and we can scale them, and they satisfy the rules of vector spaces, they are vectors. So it's kind of like, if it walks like a vector and it talks like a vector, then it's a vector. Functions do walk and talk like vectors. Or I guess the expression should be, if it adds like a vector and it scales like a vector, then it's a vector. And functions do indeed. Okay, so to make the analogy maybe stronger, let's think about what is a column vector. Like, say you have this column vector consisting of a bunch of numbers. Like, let's just call them x1, x2, x3, and there's like 100 numbers in there, x100. So this would be a vector in R100. You could imagine it as some arrow emanating from the origin in 100-dimensional space. In terms of data, a way of thinking about what this is you can think about it as an assignment. Think about it this way. An object that assigns to each number in the list of numbers 1, 2, etc. up to 100, a real number. So assign to each integer, 1, 2, 3, etc. up to 100, a real number. So to 1, we assign it the real number x sub 1. To 2, we assign it the real number x sub 2, and so on. So you can think of these actually kind of like functions. input an integer from 1 through 100, and it outputs for you a real number. It's a real valued function of an integer variable, where the integer is allowed to range from 1 through 100. You can even imagine plotting it. So 1, 2, all the way up to 100, and then you can put a dot for the different values. So x sub 1, x sub 2, x sub 3, x sub 4, then you get 100 of these dots, and this bunch of dots would be like a plot that represents this one object, this one 100-dimensional vector. And so you now have two ways to imagine what this thing is. You can imagine that it's a point in 100-dimensional space, or an arrow emanating from the origin to a particular point in 100-dimensional space, or, that's pretty hard to imagine, right? Or you can imagine it as a plot with 100 possible input points on the x-axis. I guess I should call it the n-axis, if you call these individual entries x sub n. Yeah, so you can imagine that this plot basically is the vector. Maybe a smaller example. Take the vector 1, 2, 3 in R3. You have two ways of thinking about it. On the one hand, you can plot it as a point in the three-dimensional space x1 with axes x1, x2, x3, and just go like, okay, x1 is 1, so I'll go out 1 unit that way, x2 is 2, so I'll go out 2 units that way, and then x3 is 3, so I'll go out 3 units that way, and then it's this dot, or an arrow pointing to it, coming out of the origin. So that's one way of visualizing this. On the other hand, you can visualize it as a plot where there are three, if you think of these entries as x sub n, x sub 1, x sub 2, x sub 3, there are three n's, 1, 2, 3. And for this particular vector, in position 1, we seem to get value 1. In position 2, we seem to get value 2, and in position 3, we get value 3. So just 3 dots. So it's like a function. So already, the vectors that are column vectors, you can actually already think of them as functions. And all that's changing now, when you look at a function of t, is that the input is allowed to be, instead of having to be discrete like this, the input is allowed to continuously vary. So we're including the stuff in between. So we're kind of going from, as we go from column vectors to functions, we're kind of going from from x sub n, which is like x as a function of n, x sub 1, x sub 2, x sub 3, etc. We're going from that to x of t. And they're really similar. I mean, we just, by convention, we choose to write this as a subscript and this as not a subscript. But you could write this as x of n, and you could write this as x sub t if you want to. So that's not too important. It's just the thing that it's a function of now doesn't need to be an integer. Now it can be any, it can vary continuously. So a function like, I don't know, e to the t, consists of all of these infinitely many dots. And so you can think of it as an infinite dimensional vector. And it's more than just an infinite list. In fact, it's sort of continuous, right? So it's like between 1 and 2, even between position 1 and position 2, there are infinitely many points where it takes values. And this is much harder to visualize in this kind of form, where you stick it where you try to imagine that x of t is one point in a space. That's pretty hard to visualize it that way. I mean, it was already hard with a point in R100, right? We basically only visualize it by using analogy. We imagine something in R3 maybe, because we can imagine 3 dimensions. And then we just think, well, just that picture, but more. Whatever that means. For this, if you want to imagine it as a point, or as like an arrow from the origin to a point in a space, that space would be not 100-dimensional, it would be infinite dimensional. So that's what people mean when they say that these functions are living in an infinite dimensional vector space. They are vectors in an infinite dimensional vector space. Okay, despite all of the difficulties with visualizing points in infinite dimensional space, the linear algebra theory is pretty simple and applies to functions in the same way that it applies to these kind of column vector things. There are some things that don't work in infinite dimensions, but most of the basic ideas are okay. So, okay, back to the original question. What do I mean when I say these functions are linearly independent? So I'm just going to use the meaning of, I'm going to use the definition of linear independence from linear algebra. Hang on, let me rearrange the board here. Okay, so from linear algebra, two vectors, v1 and v2, are linearly independent if whenever a linear combination of them equals the zero vector, we must have that the coefficients are zero. So this is kind of a nifty and clean way of saying that no one of the vectors in the list is a linear combination of the other vectors. So there's no redundancy. If you try to use the list and take its span, take the span of this collection of vectors, take the linear combinations, then there's no redundancy. Every vector was needed. There's no vector that was already captured in the span of any of the other vectors in the list. All right, so this is the definition. So when I say these are linearly independent, this is what I mean. So to prove to you that they're linearly independent, I will say, suppose that c1 e to the lambda 1t plus c2 e to the lambda 2t, what happened? c2 e to the lambda 2t equals 0, the zero vector. The zero vector is the zero function. So the function with a plot that looks like that. When you plot x of t against t, it looks like that. So suppose this is true. Now when we suppose this is true, we're supposing it's true for all t. Right? Just like when we suppose this is true, where we're thinking of v1 and v2 as column vectors, it's actually a list of equations, right? If v1 and v2 are column vectors in R3, then this is actually a list of 3 equations, right? An equation happening at each entry. Similarly, this is a list of infinitely many equations, one for each value of t. So when I say suppose this is true, I mean suppose it's true for all t. For all possible t. Okay, then can I prove to you that c1 and c2 are 0? So here's a way to do it. If this is really true for all t, then I can plug in any value of t that I want, and it should be true for that value of t. So I'm going to plug in t equals 0. At t equals 0, we see that we have c1 plus c2 equals 0. Right? So that puts a heavy restriction on c1 and c2. if C1 and C2 are to have the property that C1 times this vector plus C2 times that vector equals 0, then they must have opposite sign. C1 must be negative C2. So then for all t, we have C1 e to the lambda 1t minus C1, so I'm replacing C2 by negative C1, e to the lambda 2t equals 0. Interesting. Now, we are trying to prove that C1 and C2 are 0, right? So if C1 is 0, we are done. That's because if C1 is 0, then C2, which is negative C1, is also 0. So if C1 is 0, we are done. If C1 is not 0, then we can divide by it in this equation. So then we have, divide this equation by C1, and let's move one term to the other side. We have e to the lambda 1t equals e to the lambda 2t. Right? But let's see. Try plugging in t equals 1. So at t equals 1, we get e to the lambda 1 equals e to the lambda 2, right? Now take the log of both sides. Taking log, lambda 1 equals lambda 2. But we had assumed at the beginning that lambda 1 and lambda 2 are different. So you see, having C1 not be 0 leads to lambda 1 equals lambda 2. So that means it couldn't have happened. It must be that C1 equals 0 if lambda 1 and lambda 2 are really different. So that is the proof that these two functions, e to the lambda 1t and e to the lambda 2t, are linearly independent. And the practical use of this is that you will know, when you are in this case where your lambda 1 and lambda 2 are different, you will know that you have a way of writing the general solution, C1 this plus C2 that really is general. So you will be able to use it to make predictions regardless of what the initial conditions are. On the other hand, if we did not have this linear independence, which would happen, for example, if lambda 1 equaled lambda 2, then you would not be finished. You would know, hey, I haven't found enough solutions. If I write C1 this plus C2 that, that's not general. That's not general enough. There are some initial value problems that I still cannot address with that situation. Okay, so that's it for the optional video. And in the next one, I'll go back and look at... actually, I think what I'll do in the next one is do an example. This has been all pretty theoretical so far.